Okay, so welcome to the lecture of this finite volume method. Now, for different schemes, what are the values of this? So, again this would be on uniform grid and what you get uniform grid the psi r diagram, then the upwind scheme that has m and n equals to 0 and 0, second order upwind scheme which has 1 0, central difference scheme has m n equals to 0 1, from has m n equals to half, then you can have quick which has the m and n 1 by 4, 3 by 4, downwind scheme which has values 0 2, then you can have the other like Osher where the Mn has 3 segment, one is 1 0, 0 2, 0 0 which is Rf less than 2 greater than 0, Rf greater than equals to 2, Rf less than 0. Now, muscles, the Mn has 4 different segment, 2 0, half, 0 2, 0 0, where Rf goes between 1/3 0, Rf goes 1/3 3, Rf greater than equals to 3, Rf less than 0, and super B which is given as in again 5 segment, one is 2 0, 0 1, 1 0, 0 2, 0 0, where Rf less than half greater than 0, Rf less than 1 greater than half, Rf less than 2 greater than equals to 1, Rf greater than equals to 2, Rf less than equals to 0. So this approach is similar to your NVF, NWF so there is an approach which is similar to that NVF, NWF can be implementation of the similar TBD based NWF. So one can implement in the similar fashion. So that actually talks about different class of higher order high resolution schemes and their improvement, and then looking at the corrections. Now the point comes when use these things finally in the convection term, because we are in the framework of convection diffusion system, the boundary condition becomes then important element. Now the boundary condition for the convection terms are generally much simpler than for the diffusion term. Why? Because typically the boundary condition which you encounter are inlet where some velocity would be given, outlet, wall where no slip boundary condition would be given, that means then symmetry. Now, typical boundary elements which one can see now here in this particular unstructured element, this is an unstructured elements, you can see the boundary element. So, this side is the boundary side. So, this particular, this is the boundary, and all these elements are exposed to this, or rather this face which are exposed to the boundary face. So, these all these elements are exposed to the boundary face. Now, you have the discrete values of phi which are stored at the cell centers. Now, but one has to calculate this SB denotes the boundary vector, surface vector B is the boundary face. Now, this C is the centroid of the boundary elements, and so this face B which is actually exposed to the boundary. So, and SB which is the surface vector pointing outward. So, the discretization of this particular cell would now become, for any dimensional system, in a generic system it will become F NBC J C dot SF equals to 0. So, JC stands for convective flux only. So, the interior faces are also discretized using the similar expression, but they are independent. So, any interior faces are also can be discretized using the same expression, but they are free from these boundary elements. Now, here one face is exposed to the boundary. So, this flux which is shown here, it has to be properly represented for this boundary. Now, when you talk about that particular flux at boundary B, one can write this would be the convective flux or the component of the flux. This is rho V phi at these boundary faces. So, such that this JB C dot SB which will become rho V phi B dot SB, and one can say at this face it is the flux M dot phi B. Now, if you implement this in this discretized system, so this will become now surface integration of rho V phi dot S at faces plus rho V phi dot S at B equals to 0, where F refers to the, maybe one can say this is F1. So, F1 refers to the all interior faces. For this particular element C, this one, this one, this one and this one are the interior faces, and the fifth phase is the boundary phase. Now, the specification of the boundary condition involves either you specify the value or unknown boundary value phi b, or one can specify the boundary flux. So, depending on that, this particular discretization equation or discretized equation needs to be modified. If the boundary value is known, that is what we call it is a Dirichlet kind of boundary condition, and that we have already seen how to implement that kind of boundary condition. So, if the surface flux is provided, then that is known as Neumann conditions or the gradient conditions. Now, that is the formulation at any inlet boundary. Now, we will look at the inlet boundary conditions. So, inlet boundary conditions. So, this is for convection flux. So, that is the boundary phase, and the inlet through this phase goes in this direction. The normal is this direction, this is the surface vector, and the connection between C and B is this line along EB, and this is perpendicular to that. So, this already we have considered that slightly the centroid is slightly off. So, here in this domain you can say that phi is either specified, since the inlet boundary condition for convection it is dependent on the velocity field. So, most of the time the velocity field is known. So, which means if the velocity is known, that leads to that the flux is also known. If you know the velocity, then you can also say the flux is known. Now, once you look at the discretized equation, this would be F1 NBC rho V dot S F1 equals to minus rho V dot S B phi B, which is minus m dot B phi B. Now, in any high resolution scheme is used to discretize the convection flux at the interior faces. I mean, assuming that one has used the HR scheme for the interior faces, then is implemented via deferred corrections approach, then the modified algebraic equation for the boundary element could be written as A C phi C plus F goes over the element equals to B C. So, that means my AF is flux FF, which is minus F dot 0, AC is summation over all the faces of flux CF, which is going over all the faces m dot F 0. Now, one can write minus capital F NBC A plus F m dot F, and then B C equals to minus flux V F, which is m dot B phi B minus F n B C m dot B minus phi F H R minus phi F upwinds. So, this is my term due to deferred corrections, where F refers to the interior neighboring nodes of the C, and here one can say this could be also F1, then that makes life simpler what we are doing. This F1 is the interior faces of boundary element. So, now that is how you implement the. Now, if you go to outlet boundary condition, so that is an outlet. So, outlet, the flow goes in the outward toward that, and this is the cell C. So, outlet, no information from the downstream of the boundary grid point is available. So, that means if this is the boundary face, then you do not have any information from this side, everything whatever is interior, one has to use that to get this. Now, because of this directional phenomena, the phi value at the boundary is highly dependent on the upstream location, because at the outlet the flow has to go outward. So, everything will be heavily dependent on the information available at the upstream locations. So, in fact, the upwind and the second order upwind scheme, for example, it do not require any information at the outlet, since all its value can be expressed as a function of the value at upstream. So, if you look at pure first order upstream and second order upstream, they use all the information from the points which are sitting ahead of it. It does not require anything at the downstream information, but the treatment that has to be proven to be very effective at the outlet boundary condition is to assume that phi profile is either fully developed, which is equivalent to that del phi dot n at the boundary should be 0. That means no gradient at the boundary. Usual practice at the outlet is to apply the upwind scheme, where phi B should be equals to phi C. Now, similarly, you discretize the convective flux, or for the interior elements we are using, these are interior elements. If you use for high resolution scheme, then the modified algebraic equation for the boundary element would be using some deferred corrections. So, the equation will look AC phi C plus F NBC AF phi F equals to BC. Now, here again the AF would be flux FF, which is minus m dot F 0, AC is F1 NBC, because F1 only. So, this is the phase which we are interested, because that is the boundary phase. Now, F1 AC will get information for all the interior phases, these are the. So, this is all are belongs to interior face. For example, this is F1 prime, F1 double, F1 triple, F1 fourth. So, 4 interior faces are there where these fluxes need to be calculated, which will become capital F NBC A plus F1 goes NBC m dot F plus m dot B, and BC, which can be represented at F1 NBC flux Vf, which is minus F1 NBC m dot F phi up HR minus phi F upwind, which is again the boundary condition, boundary value for the deferred corrections. Here also F1 refers all the interior faces of the boundary element, and C is the element which is concerned or the owner, and F is all other elements or the neighboring elements, and the boundary, it says the gradient is 0. And then, so we have looked at the inlet, we have looked at the outlet. Now the other one which we can see is the wall boundary condition. So the wall boundary condition, which is essentially at the solid wall, typically fluid flow problem, it is a no slip wall, which means this is the surface which is the wall. So it is a wall boundary condition. Again, this is the cell C, interior cell, and this is the wall. So wall boundary condition, actually no slip boundary condition says velocity components would be 0, at the wall would be 0. That means whatever velocity component, if it is a multidimensional system, you have u, v, w, they would be 0. So as such, convection flux, that means this will lead to convection flux to be 0, and that does not appear in the algebraic equation. Now again, similarly, if you are using for any interior nodes the high resolution scheme or HR scheme, then when you come down to boundary, you need some corrections, and or rather to adopt a high resolution scheme at boundary, need to have deferred correction approach. Okay. So the modified algebraic equation for the boundary element, this C, which will look like AC phi C plus F goes over NBC AF phi F equals to BC. So the coefficients, they would be now can be evaluated, where AF equals to flux F which is minus m dot F 0, AC which is summation over F1 means all other interior faces. So this could be F1 1, F1 2, F1 3, F1 4. So there are 4 interior faces which can be used for this calculation, which is summation over f1 goes, which is m dot f 0. So, if you rearrange that, so you get back the summation over neighboring cells with AF plus f1 goes over the interior faces m dot f, and the right hand side term would be minus f1 goes over all these faces VF, which is f1 NBC m dot f phi f HR minus phi f upwind, which is again the term arises due to deferred corrections, and f1 here, which also refers to the all the faces belongs to the interior faces, and C is the cell which is concerned or the owner cell, and F are all neighboring cells. Now, there could be one more condition which you can look at is the symmetry boundary condition. In symmetry boundary condition, which means the if this boundary is a symmetry boundary of a element, nothing crosses across this boundary. So, no flow across that boundary. So, whatever is here, it should be exactly similar to that side. So, it is treated in a similar fashion to the wall boundary condition, where the flux, convection flux normal to the symmetry boundary said to be 0. So, three different kind of boundary conditions we have looked at it in respect to the higher order discretization. So, when we started with the convection discretization, we had looked at all these inlet boundary, outlet boundary, symmetry boundary, wall boundary conditions, but that was with respect to our initial discretization scheme. Now, what we have looked at here is that for interior node we are using the higher order schemes or higher resolution scheme. So, obviously, when you come down to boundary, you do not have the information from the other side. If this is the boundary, you do not have the information from this side. So, to apply the HR scheme, you require some sort of an modification to that, which is the deferred corrections, and which will come as a source term in the discretized equation. So, with that objective, like the application of HR scheme to be consistent with your all interior discretization, we looked at the different boundary conditions. So, the first one we looked at inlet, where you come across all these coefficients and you can see the corrections which arise due to the deferred corrections. Similarly, you come to outlet, where no flow crosses the boundary, and final equations or the source term will have some deferred corrections. So, that allows you to, and the third one at the wall boundary, where the no slip boundary condition is satisfied, where it means the convection flux is 0, also come across these deferred corrections. So, you can be consistent in application of the HR scheme at interior node and the boundary node, and that concludes the discussion on the HR scheme. So, we will stop here, and the next class will take it up from there. Thank you.